Let's talk just a little bit about where some of these antiderivatives or derivatives come from. Suppose we have the derivative with respect to x of, let's take 5x. Okay, well we know that this is just equal to 5. But we could also write this, right? I mean, isn't this true here too, that also the antiderivative of 5, it could have been this. It could have been 5x plus 1. It could have been antiderivative of 5 with respect to x could have been 5x plus 2. In fact, right when we differentiate, those things, those constants just become 0. So I could put any number at all I want out there. So we could write this. The antiderivative of 5 dx is equal to 5x plus c, where c is called just an arbitrary constant. Could be any number at all. So let's make a general statement here. If you differentiate with respect to x some constant times x, what you get is that constant. And if you antidifferentiate that constant with respect to x, you get kx plus c, where c is that arbitrary constant. So you get back not just to a particular you don't get back to just a particular function, but you get back to a member of the family. You get back to a member of the family of functions. Now, how about this one? What if we take the derivative with respect to x of x squared? Well, we know what happens here, right? The exponent comes down as a multiplier, and then we decrease it by 1. So we'll have 2x. Now what we want to do is antidifferentiate that 2x with respect to x. So what are we going to do? Well, we're going to have the 2. Now the x, what happened? That exponent was decreased by 1, so we're going the opposite way, so we'll increase it by 1. So it's 2x to the first plus 1. But then we have to eliminate that 2. So since the 2 came from the exponent, now got multiplied, we have to undo the multiplication with a division. And then plus c. So those go out, and we end up with x squared plus c, right back to the family. So what about this one here? What if we take the derivative with respect to x of, say, x cubed? Well, we know what happens. The 3 comes down as a multiplier. We decrease it by 1, so we end up with 3x squared. And then if we go backwards, right, we antidifferentiate 3x squared with respect to x, we're going to have 3, and then since we decrease the exponent by 1, we're going to increase it by 1. Now we have to eliminate that 3, right, because we multiplied by 3. We're going to have to divide by 3 to undo that multiplication. Plus c. So the 3's cancel, and we get x cubed plus c. So we don't get exactly back to x cubed, but we get back to that family. So ... here's what that would take us. If we antidifferentiate x to the k with respect to x, we're going to get x to the k plus 1 over k plus 1 plus c. So for example, if we antidifferentiated, say, x to the 4th with respect to x, we increase that exponent by 1 and divide by that new exponent. And here's another one that we've done. We take the derivative of e to the x, right? This is a nice one because when you differentiate e to the x, you get e to the x. So if we go backwards, antidifferentiate or integrate e to the x, we get back to e to the x almost, right? But we get back to e to the x plus c. Well, and then how about this one? When we differentiate with respect to x, if we differentiate that natural log of x, what we got was 1 over x. So if we go backwards and we see this one, what we're going to get is a natural log. Now we actually get the absolute value of x plus c. And let's finish it off with something like this. You know, if you've got the derivative with respect to x of a constant times some function, now the function might be, you know, the function might be e to the x, it might be 1 over x, it might be x cubed, could be a 7. but you have a constant times a function. This gave us the constant times the derivative of the function. So what we can do now is this. If we have the integral of a constant times some function, well, we can just bring that constant along and then try to integrate or anti-differentiate that function. So for example, if I had this, if I want to anti-differentiate, say 7 e to the x with respect to x, I'm going to get 7 integral of e to the x dx, which is just 7 e to the x plus c. Now, I don't really need to write that step. I know what's going to happen. So I can go from here to here. Likewise, what if I'm given this one, the integral of, say, 7 over x dx? Well, if I look closely, that's really like 7 is the integral of 7 times 1 over x dx. I can bring that 7 along, and then I get 7 natural log of the absolute value of x plus c. So I don't really need to write, I don't need to break it up like this. I'm just showing every step. Once you do a few of these, you can go here, from here, directly to here.